Hi guys, we're now going to solve problem 2. Consider the reversible elementary gas phase reaction shown below that occurs at 300 Kelvin in a constant volume reactor of 1 liter, where K1 is 6.0 liter per mole per hour, which is the forward reaction constant, and K2 is 3 per hour, which is the reverse reaction constant. For an initial charge to the reactor of 1 mole of A, 2 moles of B, and no C, find the equilibrium conversion of A. So we are given with the values of the two reaction constant, or the two rate of reaction constant, and the values of A, B, and C. This problem is an example of a second order reversible reaction. So to solve for the unknown, which is the equilibrium conversion of A, we need to derive first the rate of equation of a second order reversible reaction. To do that, let us first write the chemical reaction. A plus B reversible C. Find what is asking the problem is the equilibrium constant, or equilibrium conversion of A, or we can write that as XAAE. So now we derive the rate of equation of the second order reversible reaction. Negative dCA over dt is equal to K1, the two reactants, Ca times Cb minus K2 times Cc. We all know that the concentrations of A, B, and C changes with time. So we can rewrite this term into this. With respect to reactant A and the conversion of A, we can write it as K1 times CaO minus CaO XA times CbO minus CaO XA minus K2 CcO plus CaO XA. Now, this is minus because we all know that this is as time goes on, the reactant will decrease. So from the original concentration of A, we subtract it with the percent conversion of A times its concentration, original concentration, and same case with the reactant B. And on the other hand, with respect to C, which is the product, we use plus because the product is increased as time progresses. So we add the percent conversion of A times the concentration of A at its initial point. So now let us consider the equilibrium point of A. Note that at equilibrium, the concentration of A no longer changes with time. Therefore, we can write dCA over dt equal to 0. So we can equate this whole term here into 0. Therefore, K1 CaO minus CaO XAE. We will make XA into XAE since we are now talking about the equilibrium state of the reactant A, times CbO minus CaO XAE minus K2 CCO plus CaO XAE equals to 0. Now we're going to do the math here. We are now going to transpose K2 to the right side. K1 CaO minus CaO XAE times CBO CaO XAE equals K2 times CCO plus CaO XAE. So we will now we will combine all rate constants and all concentrations of A, B, and C. So we'll transpose K2 into the left side. We have K1 over K2 is equal to CCO plus CaO XAE all over this CaO minus CaO XAE times CBO minus CaO XAE. So this is the resulting equation. Now let's inspect our given based on this equation. K1 is given. K2 is also given. CA, CBO, CaO, CBO, and CaO are also given. Therefore, we are left with this variable. So the only variable here that has no value is XAE. So we can now solve for the conversion of A at its equilibrium point. So we copy first K1, K2, CCO plus CaO XAE all over CaO minus CaO XAE times CBO minus CaO XAE. So we are now going to substitute the given. K1 is 6.0 all over K2 is 3.0. CCO is, based on the given, it is 0 plus CaO is 1.0 times XAE all over CaO, which is 1.0 minus 1.0 XAE. CBO is 2.0 minus 1.0 XAE. So we'll do the math here. We have 2 and we have XAE. We can neglect this coefficient since it's just 1. So 1 minus XAE times 2 minus XAE. So going to simplify this and make this a quadratic equation. We have 2 is equal to XAE minus XAE times 2 here. I'm just copying the previous part. XAE. So we're going to transpose this. First, we're going to combine this denominator into 1. So we have 2 minus 3 XAE plus XAE squared. So we have XAE here too. We're going to transpose this denominator into the left side. So we have 4 minus 6AE plus 2XAE squared equal to XAE. So after that, we are going to combine like terms. Combine this and this. Therefore, we have 2XE squared minus 7XAE plus 4 is equal to 0. So this is now a quadratic equation. So for the value of XAE, we're going to use, of course, calculator. We press mode, then 5, then 3, and input the coefficients of the quadratic equation. 2, -7, and 4. Therefore, the values of XAE is, or are, XAE, these are the values 2.7808, and XAE is equal to 0.7192. We all know that conversion of a reactant does not exist the value of 1. Therefore, we neglect this value of XAE. Therefore, our final answer is 0.7192, the conversion of reactant A. Thank you for listening.